Hi again. In this video we're gonna focus on the classification of discrete time signals. It means that I will define discrete time signals, its energy, its power, if any, and we're gonna define the mathematical properties that can be used to determine the signals and compute them. So in its most general form, a signal, it's just a sequence of numbers. These numbers can be either real, either complex, but the most important part is that these signals are indexed by integers. These values are indexed by integers. So in this sense, you can define a discrete time signal either by a straightforward equation, something like this. Okay, so it means that x of 0 will be equal to 2, x of 1 will be equal to 5, and so forth. So this is like a direct definition of a signal. This signal can be based on usual calculus functions, like, cosinus. You can also, by the way, define signals recursively, something like that. Okay, and in that sense the definition is less straightforward, but this is one of the most important definitions in signal processing, in the sense that it defines what is called the difference equation, and difference equation is one very important part of digital systems. So the definition itself, it is not very difficult. You must pay attention to the use of squared brackets, which is mandatory in the field, okay? In the sense that when you're using regular brackets, regular parentheses, we are talking about a continuous free variable. So this is a continuous time signal, something like that. And when you're using squared brackets and n instead of t, this can be understood as a discrete time signal. It's a matter of notation, but it is a commonly accepted notation in the field, so we need to be completely clear with that. In a similar way that we define the energy of a continuous time signal, you can define the energy of a discrete time signal as the sum of the squared values with the absolute value. The absolute value, it is for the case when the discrete signal has complex values. So you must take the radius of this complex number and put the power of 2, and then you must sum it. Okay, it shares a bit of similarity with the norm of a vector for obvious reasons. Okay, so the energy of a discrete signal can be understood as the extension of the norm of a finite dimensional vector. There is an interesting property for continuous time signals, stating that if a continuous time signal is bounded in time and in amplitude, then it has necessarily finite energy. Okay, the same property also exists for digital signals, but it is even simpler than that, because if you focus on a closed interval, okay, of integers, and you assume that the signal is defined in this interval, then all the values of the signal in that closed intervals are finite. So it means that if your signal, your discrete time signal, is bounded in time, it necessarily has a finite energy, and signals with finite energies are called energy signal. Okay, so energy signal is mostly a signal with finite energy, And in that context, it is super clear why this remark makes sense, because if your signal is bounded in time and naturally it is bounded in amplitude, then the infinite series that you have above is in fact a finite series, and it necessarily converges to a finite value. Okay, for example, let's say that we define both the signals, this one which will be equal to 1 from 0 to 10 and equal to 0 otherwise. So this one is an energy signal based on the previous remark. Okay, you can see clearly that it is finite in time and also in amplitude. On the other hand, this will later on define it as a digital step function, is not an energy signal. So x2 here is not an energy signal. In order to prove that, just need to write the definition. Remark that the sum in fact starts from 0, okay, and in that case from 0 to infinity, x2 is equal to 1, and the general term of the series does not converge to 0, so this series does not converge to a finite value. Okay, just to make it clear, the previous signal x was an energy signal due to the previous result. And later on we will also see that you can define the energy of a signal in the frequency domain by means of Parseval equality. So this is for the next chapters, okay? And in the same way that we define the energy of a discrete signal, a discrete time signal also can be characterized by its power, and its power is defined by this sum from minus n to n of the radius of xn squared divided by 2n plus 1, which is exactly the number of terms included in this series. So px can be seen as the same information than the energy, but normalized in time. So it is easier to get a finite power than a finite energy, because using this definition, if you have a series which diverges but with the same rate of convergence as n, so it means that the power can remain finite. And a signal with a finite power is called a power signal. In the previous class of signals and systems, we saw that a signal can be characterized either by being an energy signal or a power signal, or neither this nor that. The same characterization also exists for discrete time signals. It means that either a signal is an energy signal, so in that case it means that its energy is finite and its power is equal to 0. A power signal, and in that case the associated energy is necessarily infinite, or neither this nor that, and it means in that case that both energy and power are infinite. So as an example of power signal, we can take the same example as before and say that this step function, okay, it has finite power, because if you look at the definition and you want to investigate whether this term converges to a finite value or not, okay, so this sum is equal to the sum from 0 to n divided by 2n plus 1 of xk. Because all of the terms are equal to 1, it means that you have here a sum from 0 to n of 1. So you have n plus 1 terms divided by 2n plus 1, and you can use any calculus rule you want for that, but it tends to 1/2 as n tends to infinity. So the step function, as in analogous system, the step function has finite power. To conclude this video, and we will continue to investigate the properties, the mathematical properties of discrete time signals in the next one. I just want to define some very common signals that appear from ages in the field. Okay, so in any exercise you will find something like that. You will have you can define the delta, the Kronecker impulse signal, which is basically the equivalent of Dirac's delta function in the discrete time. Okay, it is equal to 1 for n equals 0 and 0 anywhere else. The digital step is defined as 1 for every positive n, non-negative to be more precise, and 0 for all negative n. And we can define the family of exponential signals the same way that we did for analog signals, with a slight change of notation. As you recall, exponential signals in continuous time were defined as an exponent of st, okay, where s was a complex number. In DSP, it is more common to define exponential signals as z0 at the power of n, to make it more fitted to the Z transform that we will learn in the next chapter. Some recalling the properties of analog signals, remember that the step function is in fact the integral of the Dirac's delta function. A similar property also exists for digital signals, in the sense that the step function can be written as the accumulation of the values of Kronecker's signal. Okay, this is pretty straightforward. For n, which is negative, then all the values of a delta included in the summation interval are equal to 0. So the global sum will be equal to 0. On the other hand, when n is positive, the summation interval includes n equals 0, and it means that all the value will be equal to 0 besides 1, the centered one, which is equal to 1. So eventually you get to the conclusion that this sum on the right hand side is equal either to 0 when n is negative, either to 1 when n is non-negative, so it is the digital step. And similarly, you can write delta as the difference between u and its shifted version, okay, so that only the values at 0 remains. Thanks for watching, and in the next video we're going to talk about the mathematical properties and mathematical operations that I can do on discrete time signals. Thanks and bye.